Good evening, everyone. This is the NPTEL course problem solving session. The course is Fluidization Engineering by Professor Subrata Majumder. So, the problem solving session is handled by Ankar Kartiga. That is me. I am a research scholar from the IIT Hyderabad from the Department of Chemical Engineering. So, basically you have added to the NPTEL course, that is Fluidization Engineering. So every week, till the course is completed, we'll have problem solving session where we discuss the problems associated with that week's lecture and how to solve the problem so that it would be helpful for you people when you are solving the assignments. So in a similar way, you can also have, like, if you have any doubts at any point of time, you can just ask them in the immediate time, or else you can ask at the end of the session also. So if you have any doubts from this week that you are getting after some point, you can also ask after some time, like that is next week. In the next week tutorial or problem solving session, you can ask the previous week doubt also. So this is the first session for this course. So let it be an interactive session rather than a one-way uh, interaction wherein only I communicate. So if you have any points to add, you can always add into the session. So we'll just this video will also be available in the YouTube, so you can at any point of time you can view this. So the link will be provided by the NPTEL. So yeah, we'll just start with the session. So basically, before moving into the course, we can just have a course layout wherein the course is a 12-week course. We are going to study about the fluidization phenomena. Fluidization, as we all know, it is a phenomena wherein we make the fluid to pass into the packed bed, thereby making the particles to behave as a fluid. So in order to understand this phenomena, there are so many underlying things that are happening inside, like the fluid particle interaction, particle particle interaction, everything. So completely understanding this itself is a very tedious task. So in one first 2 weeks, the course will be dealing about the introduction to the fluidization and the particles behavior, the particle properties, and the advantages and disadvantages associated with the fluidized bed. Why we are moving to the fluidized bed, and what are all the disadvantages that would be when handling the fluidized bed, and also the industrial applications associated with the fluidized bed. In the next week 3, we'll be having the characteristics of solids and solid classification, and also characterizing the flow characteristics and its outline in different types of fluidization. We all know fluidization is a phenomena wherein by varying the velocity we can understand the different modes of fluidization that can be studied within a system. So that would be dealt in the week 3, followed by week 4 to 5, wherein we will be dealing about the flow pattern inside the fluidization, like a transition and the pattern map, and also the pressure drop and different models to analyze the pressure drop and solid movement inside the bed, for like with different types of movement and different particles in the system. There may be a complete mixing inside the system, or there can be a complete segregation in the system. So all these would be studied in the week 4 to 5. And in week 6 we have gas distribution. How in if we consider the fluidization wherein we have a gas distributor at the bottom, through which we pass the fluid, that is gas, right? So depending on the application mode, we can have different types of distributors. So, and also it can vary with the small scale setup as well as the large scale industrial setups. So in industry, the fluidized beds are being used very widely. Therein we require a completely suitable design to be used in the industries. So all these would be studied in the week 6. And as week 7 is bubbling fluidized beds. As I told, depending on the fluid velocity, the fluidization would be different modes. And bubbling fluidized bed is a one type of fluidization. Depending on the particle size and particle density and how the velocity is varying. So based on this, the bubbles would be forming inside the fluidized bed. So that bubbles would in turn affect the gas interchange and mixing characteristics. Like depending on the bubble movement, the solid pattern or the solid flow inside the bed would be affected. So that is for week 7. And in week 8 we study entrainment and elutration from the fluidized beds, and in week 9 it is associated with attrition and the models, and in week 10 to 12 we have the mass transfer phenomena and the different models that are available to study the mass transfer that is happening within the fluidized bed. And also in the last week the main focus is on heat transfer phenomena. That is in here fluidized bed, it is mainly used uh, so that the one advantage is that we have a uniform heat transfer or heat distribution in the system. So the heat transfer phenomena inside the fluidized bed would be studied, and the design of the fluidized bed reactors designed for physical operation, catalytic and non-catalytic system. So basically the thing is, depending on the application, the bed would be designed accordingly. So all those things would be studied at the end of the session, end of the course, that is in week 12. So these are all the topics that would be covered in the following weeks. So for initial thing, we are going to study about the particle properties and the fluidization phenomena and the advantages, disadvantages, application, everything associated with it. So basically the books and references for this course is Fluidization Engineering by Cooney and Levenspiel is a one good book that covers all the topics that are related to fluidization, wherein we can learn what are all the basic things that needed to be known that can be covered in that book. And the next is the multiphase flow and fluidization, continuum and kinetic theory description by D. Gidaspo. This is a book where you can if, like it covers the fluidization phenomena and the multiphase flow systems, wherein we have a solid, liquid and gas inside a system, right? So multiphase flow behavior can be understood in depth from this book, and also based on different approaches like continuum approach or kinetic theory. Continuum approach, that is by using kinetic theory. What does it mean is that in fluidization we have a particle phase and the fluid phase. So sometimes in order to during the modeling, we assume the particle phase also has a continuum description rather than taking it as a separate particle for the ease of modeling purpose. So all those things are dealt in depth in this book. And this is the LG Giblaro Fluidization Dynamics and SK Majumder Hydrodynamics and Transport Process of Inverse Bubbly Flow. So all these books can be used for this used as reference for this course. So like at fluidization is an interesting phenomena to be told, because we can it is a very small topic that is covered in the BTech course or somewhere, but it itself can be covered as a whole course. So yeah, uh, it is a very interesting thing that we can go very much in depth into it to understand the system and its scale up. Till now the scale up and the modeling is kind of uh, it is a research field where it keeps on going. So yeah, these are the references. So now we'll move on to the questions. These are a few problems that are chosen for the week 1. So basically from this, these are just sample problems that would help you people in solving for the week 1 assignment problems. So if you have any doubts in these problems, or if you have any doubts in solving the week 1 assignment, uh, the questions in the week 1 assignment, if you have any doubts, it would be answered once the assignment submission deadline is over. So before that, if you have any kind of difficulty understanding in these problems, please you can always ask in the middle also, or at the end you can ask. So the first question is, the fluidization processes are advantageous for the option A, it is good mixing; option B, more contact efficiency; option C, large scale continuous operation; or option D, all the above. So what before moving into the advantages of fluidization, we must know what is fluidization, right? So in fluidization, it is nothing but we pass the fluid inside the bed so that the particle starts behaving like a fluid. So consider this as a bed. For packed bed, what we do is that we have a packed bed wherein we pass the air. So yeah, if we pass the air at some superficial gas velocity, so in the packed bed system, we have the bed packed where the solids won't move. That solids would remain stable with uh, the increase in velocity. But there comes a point actually when the velocity is exceeding UMF. UMF is nothing but minimum fluidization velocity. This you would be studying in the further classes. So if it exceeds the minimum fluidization velocity, uh, like till that point, how much ever velocity we increase, the particles inside the bed won't start, it will not be moving, they won't start to move. So after it crosses the minimum fluidization velocity, what happens is that the particle starts moving. That is, the particles initially it would be closely packed, but once it is fluidized, the particles would be loosely packed and it keeps on and it moves according to the flow. So this is the fluidization process. So why do we go for fluidization? Because we can make a consider a packed bed wherein we pass the fluid inside the bed. For example, if it is a catalytic reaction, we want the surface of the particles to be completely exposed to the passing fluid. So if that is the case, inside the packed bed, it is not exactly possible because there is only a certain surface area of the particle that is exposed to the fluid. So we go for the fluidization phenomena where we make the particles to move. The particles would be loosely packed that at that time or very loosely packed. So the particles would be fully exposed to the incoming fluid. That is the advantages of the fluidization process. So we know that the more contact efficiency, this is a true. And the next thing is, consider if we are passing the fluid inside the fluidized bed. So depending on the velocity of the fluid, the particles would be keep on moving. So there would be a good mixing between the particles. Among the particles, there would be a good mixing. So this is also one of the advantages, and this process can be scaled up to the large scale setup. That is, it is advantageous when we are going for large scale. Consider an industrial process. So when we are passing the fluid and we are just passing the fluid and making it fluidized, right? So the good mixing and the contact efficiency, everything is can be seen in those large scale systems also. So there is no uh, difficulty associated with it, such that we, like in some process, if it is a fixed bed or something, there are chances for hotspots or something to be occurring at some particular point. Whereas in fluidization, since it is completely dynamic system, so the large scale continuous operation is also feasible. So the fluidization process is advantageous for all these three. So the answer to this problem is all the above. So yeah, now this is first problem. We'll just move to the second problem. So saturation moisture content is defined as mm, maximum moisture material can retain without becoming a slurry, moisture at which material does not emit dust, tendency of powder to gain or lose moisture at a certain temperature, or none of the above. So basically, what is saturation moisture content? It is that, what is saturation? For example, if we add something to the system, it remains in that state without it changing its state. Like how much ever we add, the state of that particular system remains the same. That is the maximum upper limit, right? So the maximum upper limit till which it can retain the state without it deforming is known as the saturation point. So what is saturation moisture content is that the maximum moisture content the material can withstand without it becoming slurry. Slurry means it would be becoming a liquid, completely liquid plus solid system, but without it becoming the slurry, how much ever moisture content it can retain, that is known as saturation moisture content. It is simple that what we denote by saturation is that how much ever the maximum limit the system can retain without it changing its property, that is known as saturation, right? So in this context, what is saturation moisture content is that the maximum moisture content the material can retain without it becoming a slurry. So this answer to this is option A. So yeah, this is question 3. So what is the crush strength? Crush strength is the measure of freeze conditioning agents' effectiveness in preventing cold caking, particle breakage force as a function of time, rock breakage strength required for the crusher, or none of the above. So here, what is the crush strength? It is that the particle breakage force as a function of time. What is crush? Like it is like we are applying some force to break the particles. Or else we can say that um, if we are applying a force to a system, like for example, consider a small cube, we are applying force to the system. So at some point, like if we keep on applying the force, at some point the material would break, right? So that is the crush strength, like how much the material can withstand before it is crushing. So how can we define what like what it measures is that particle breakage force as a function of time. For example, like this is a crush strength. What is crush strength is that for example, take a rock. You are putting some pressure on that rock for a continuous period of time. Like when you keep on putting pressure or putting force on that particular rock, there is always a point after which it breaks, right? So what it is happening is that till certain point of time it is enduring that particular force, after which due to continuous application of that particular force it is getting broken. So that it is a measure of the particular particle breakage force, that is a function of time. So the answer to this is option B, that is crush strength is the measure of particle breakage force as the function of time. So now we'll just move on to question 4. Okay, question 4 it is particle size and concentration have a direct effect on catalytic reactivity or dissolution rate, flowability and handling of granules, stability in suspension, all the above. So by seeing the question we can say all the above, but we'll just see how it is applicable to each of the options given below. Like for example, particle size and concentration have a direct effect on what are all the properties. Uh, so the first one is the catalytic reactivity or dissolution rate. Catalyst reactivity or dissolution rate. So what does catalyst actually mean? It is catalyst is just it enhances the rate of the reaction, right? So that is the catalyst. How its reactivity would be? It is the it depends on the surface area of the catalyst, right? So how much surface area the catalyst has, depending on that the catalyst reactivity also would vary on how much like vacancy it has on each of the position. All those things would come into play in that particular topic, but in general the particle size So the particle size and concentration have a direct effect on catalyst reactivity, right? For example, if the particle size is very low, and there are chances that for it to have a large surface area, I mean, they, if it is a very small particles, they have a large surface area, and the catalyst reactivity would be improved in that case, depending on the material, but it is material specific. But general thing is that catalyst reactivity is depending on the particle size, and also the particle concentration in the system also plays a direct effect. Or dissolution rate. We also know that the dissolution rate of the particle depends on the particle size, right? And also on the concentration. Like, till a certain concentration, we can dissolve the particle without any limit. Once it exceeds a certain concentration, the particles would not be dissolving in that particular solvent. So, the size as well as the concentration play an effect on catalyst reactivity of the dissolution rate, wherein like it would be directly influencing those things like reactivity and the dissolution rate. So, and also like particle, consider you are putting a very large particle into a solvent, and the dissolution rate would be very, like, it would take time than compared to the smaller particles, right? So that is the thing with option A. For option B, it is given that flowability and handling of granules. So for example, um, consider you are in a mining site or something. So in the mining location, there would be the particle or the rocks or the ores would be very larger in size, and the handling it would be kind of uh, difficult, right? And also the flowability of those particles would also be difficult, which, consider after it is it underwent the process of grinding or so, there at that time the the particle size and the concentration would just play a role, right? Because the flowability would be changed, altered with the particle size decrease, and also the handling would be very easier for the smaller particles than compared to the large size particles. For example, in the, consider the particles before breakage or before grinding, they are directly from the mining sites, wherein they would be very larger, and it would be difficult to carry out test or carry out the process with those particles, rather than with the particles that are broken down. So the handling and the flowability was much improved with the particle size, and the similar thing is with the concentration effect, and also stability in suspension. So we all know that the particle size and concentration, where the you are adding some solute or solvent, wherein the suspension medium in turn has a stability, right? That stability would be very much governed by the particle size and the concentration. For example, if you are adding something at a certain concentration, the suspension would remain as a suspension, above which there are chances for the particles to settle down. So the concentration and the size have a direct effect on the stability of the suspension medium. So the answer to this is particle size and the concentration have a direct effect on the catalyst reactivity or the dissolution rate, and also in the flowability and handling of granules and stability in suspension. All these three things are influenced by the particle size and the concentration effects and the concentration. So this is question 4. Now we'll move on to question 5. In the bulk of irregularly shaped particles, okay, there are 4 options given. We should choose an appropriate one from the that is suitable for the given question. In the bulk of irregularly shaped particles, option A, the equivalent sphere concepts work well. At least one dimension can differ significantly from that of the other dimension. Both A and B, or option D, that is none of the above. For example, the irregularly shaped particles are given by these. This is an image like A to L. We have 12 images taken from this paper, wherein it is showcasing the different irregularly shaped particles. So if we think about it, what is common in these particles is that they are not having any regular shape, and we cannot make out or pick out anything from this particles that is common amongst all these 12 particles, right? So, and one thing that is significantly common is dimension. That is, one dimension is significantly greater than all other three. Sorry, all other the dimensions. So it can be given option B, that is at least one dimension can differ significantly from that of the other dimension. So this is an answer. The first option, that is the equivalent sphere concept, works very well. So when does equivalent sphere concept works very well is that when the particles are almost symmetric or have some resemblance to be put it into the sphere. Like if we are taking a cube, like it is equi-distributed around the center of mass, similar to the concept of sphere. So we can use the equivalent sphere concept for such particles like cube, certain spheroids, and so on. Like wherein one of the dimension is not very much significantly differing from the other dimensions. But bulk of irregularly shaped particles. These are cases of one or like few cases wherein we can put use the concept of equivalent sphere. Whereas in almost most or the bulk of the irregularly shaped particles, if we denote irregularly shaped particles, what we mean is that one, like it is irregularly in shape, and we cannot use any concept to put it together, or else we, like it is kind of difficult to analyze the system. So at least one dimension can differ significantly from that of the other dimension is the right answer. And equivalent sphere concepts does not work well. For example, if you are considering this and we are denoting it by an equivalent sphere wherein the sphere and this particle has an equal volume, that is a concept coming with the equivalent sphere. But do you think that would be an proper statement? Because for example, this equivalent sphere, it is, this shape can be divided into two and it can be somewhat like this also, right? If it is the same volume as that of the sphere, both this particle and that sphere, like another equivalent sphere concept also comes into picture. But does that, for example, I'll just put demonstrate, like you have this particle, if like this is the equivalent sphere is this one. I mean, just don't consider the exact dimension, just think about it in terms of concept. So, this uh, irregular shaped particles can also be written like, I mean, if it is, this also contains equivalent, okay, oh yeah, this, and consider this and this have same equivalent volume, and this also have same equivalent volume. This also in turn has same equivalent volume, but that is not our concern. So does that mean that this particle and this particle are same? They are not the same, right? So this equivalent sphere concept does not work well in the bulk of irregularly shaped particles. Only we can use it like for a, consider the cube. In this cube, it is somewhat equidistributed among the center of mass, similar to that concept in the sphere. So in this we can use, but in most of the cases like this and all, there is always a one dimension that is greater from the other dimensions. At least one dimension is significantly uh, different from that of the other dimension. Consider this. So basically this is almost similar. So but if we consider the bulk, almost you can see, right, the bulk of is very similar. In this only few cases like this and all, we can use irregularly equivalent sphere concept. But in all, and this also in some case we can use. But in almost all other cases, the we cannot use equivalent sphere concept, right? So at least one dimension significantly different from that of the other dimension is the correct option. So now we'll just go on to question 6. For adsorption study, what type of mean diameter is important? Surface mean diameter, volume mean diameter, arithmetic mean diameter, and all the above. Okay. What is adsorption study? Adsorption study is mainly associated with studying how the particles are getting absorbed in the particular surface, right? Uh, so on looking at this aspect itself, we can say that the this concept comes into picture when we are dealing with the non-spherical particles, so that we need a certain type of diameter, right? Once again, just certain common diameter that can be put to use for the whole system. So for example, uh, we can consider a system of a handful of non-spherical particles. If we are about to describe all those particles having this much of diameter, what concept you would be using to denote those system? So there are various types of mean diameter associated to study the particles. This would always come into picture as each individual particle's diameter would be calculated, and depending on that, the volume or surface area or something, we would proceed with the calculation of the whole systems, and that is whole set of particles uh, concept. For example, for the adsorption study specifically, consider we are dealing with catalyst or something. What is the main purpose behind the study? Wherein we know the surface surface area plays a major role in adsorption study. So how much surface area it has, and that much reactivity or that much activity it would be having, right? So for this purpose, what is the important parameter that we are taking under consideration? That is the surface area. So for the adsorption study, the what type of mean diameter is important? The answer to this is surface mean diameter. Surface mean diameter is very important when we are dealing with the adsorption study. So depending on other applications, volume mean diameter or arithmetic mean diameter can be used. It depends on the application purpose only, not any other thing. All these are just few parameters that can be used to describe the system as a whole. That is for the ease of representing the system. So now we'll just move on to question 7. Particle size distributions are classified into number and volume weighted distributions, volume and intensity weighted distributions, number and intensity weighted distributions. So yeah, this concept we just saw now, it is an extension to that case. For example, here what is particle size distribution is that, consider you are going to grind a ore particles. So amongst the ore, generally what would be the representation? We would be saying this much amount of particle is less than 200 micrometer and greater than 100 micrometer, uh, and this much of particle is size is less than 100 micrometer and greater than 50 micrometer. Like that, we would be having a certain distribution set of distribution, right? So that distribution range and how it is calculated, like how can it be classified? So they can be either classified by particle size distributions or classified into, first they can be distribution can be volume based or the number based or even intensity based. So all three of the given options, like number based, volume based, or intensity weighted. For example, this much volume of particle is between minus 100, like 100 is less than 200 micrometer but greater than 100 micrometer. Or we can also say this much number of this many number of particles is greater than 100 micrometer and less than 200 micrometer, or similarly intensity weighted. So the particle size distribution can be accounted by means of volume, number, or intensity. So the answer to this is all the above. For example, the particle size distributions are classified into number and volume weighted distributions, number and intensity weighted distributions, and volume and intensity weighted distributions, and number and intensity weighted distributions. And option D is all the above. Okay. For a spherical particle, we just go to question 8. For the spherical particle, the sphericity value is equal to. So, sphericity concept comes into picture when we are dealing with a non-spherical particle. That is, the particles that are non-spherical. In order to represent those non-spherical particles by using some concept, so many parameters came into picture like sphericity, circularity, and so on, aspect ratio, everything that we use to describe the non-spherical particles in terms of some measurement to represent or in terms of spherical particles. For example, take fluidization phenomena itself. In fluidization phenomena, in general, among the literature studies, the particles that are in focus is spherical particles. For example, if in in industries the particles in the fluidized bed are not at all spherical, right? They would be irregularly shaped. In the industrial applications, when we focus, for example, biomass gasification and everything, they would be the particles associated with them would be non-spherical in nature. They can be rod shaped, they can be irregular shaped. More than we give some certain specific shapes associated with them, the almost all of them would be irregular. But to study them using some models in terms of modeling is not an easy task to represent the irregular nature of the particles. So the easiest way would be to go with the sphericity associated with the non-spherical particles. Sphericity of those non-spherical particles, put it together in the model of the spherical particles, and we can study them. That would be an approximate way, but it is not the exact way. So studies are being conducted to identify the exact study or exact way to model those non-spherical particles, but still they are in progress, right? So sphericity is one such concept to study the irregular shape of the particles. So what is the sphericity value for the spherical particles? In general, since it is for spherical particles, it is equal to 1. That we all know, but let us just identify what is the calculation behind this. So we'll just have sphericity is equal to, so it is the surface area of a sphere to the volume of sphere. That is, the sphere is the, I'll just come back, this is the surface area to volume of that particular non-spherical particle. This is the sphere wall that is having equivalent diameter, equivalent volume as that of the non-spherical particles. That is, sphericity is defined as the surface area to volume ratio of the sphere of having same equivalent volume as that of the non-spherical particles to the surface area to volume of the exact non-spherical particles. Or else, just a minute, I'll just give you a proper definition. Surface area of the sphere to the surface area of the particle is the sphericity. So it is just measure of how much spherical the object is. It is the ratio of the surface area of an equivalent volume sphere to the actual surface area of the particle. That is surface area of an equivalent volume sphere to the surface area of the particle. So the volume would be obviously equal, so they would get cancelled. So it is the surface area of the equivalent volume sphere to the surface area of the particles. Since it is an resemblance of how much spherical the object is, for spherical particles it is obviously 1. That is, so sphericity value is 1. So circularity of a particle outline is defined as the ratio of, circularity is the next concept wherein we study how much the particle is resembling the spherical particle. Like similar to sphericity, surface circularity is another one parameter. So it is just, since sphericity is associated with the volume of the particle, circularity is just associated with the perimeter or something. Like circular nature means we just associated with 2D, right? So basically, circularity of a particle outline is defined as the ratio of actual perimeter to perimeter of an equivalent volume circle, convex hull perimeter to actual perimeter of a circle, area bound by actual perimeter or area bound by convex hull perimeter, all of the above. So similar to the sphericity, circularity is the actual perimeter to the perimeter of an equivalent area circle. So this is an equivalent area of the circle, wherein the previous sphericity case we saw the volume of the particle. So this is based on a perimeter or the area concept in 2D, and that is based on 3D. So circularity of a particle outline is defined as, that is just we can see the particle outline. So it obviously comes under the 2D. So actual perimeter of that particle to the perimeter of an equivalent area circle, so that we can see how much it obeys or resembles the irregular shaped particles. So yeah, now we'll just move on to question 10. Zeta potential is, it is a measure of the magnitude of the electrostatic or charge repulsion or attraction, one of the key parameters known to affect dispersion stability, applied to improve the formulation of dispersion, emulsion and suspensions, all the above. So zeta potential, it is a measure of the magnitude of the electrostatic or charge. Zeta potential is just associated with the charges, and so like electrostatic things and all. So it is the answer to this problem is all the above. Like it is a measure of the magnitude of the electrostatic or charge repulsion or attraction, and it is one of the key parameters to affect the dispersion stability. Like for example, if I consider a suspension system wherein you are dispersing a salt or something. For example, consider sodium chloride dissolved in a solvent, that is water, wherein sodium ions and chlorine ions would be there, right? So the attraction of the if you had more sodium ions or more chloride ions, it would be affected based on the number of ions, right? So that would be given by the zeta potential, wherein one of the key parameters is known to affect dispersion stability, or it is a measure of magnitude of electrostatic or charge repulsion, and applied to improve the formulation of dispersion, emulsion and suspension. And since all these are known to influence this zeta potential, zeta potential is a measure of it is a like it is applied to all the above. That is, actual definition is the potential difference between the surface of a solid particle when it is immersed in a conducting liquid and the bulk of the liquid. Like the potential difference between the solids and the bulk of the liquid medium, that is the solvent medium. So like it is an like so much concept would be behind it, so you can just see this also. Now we'll just go on to question 11. Uniform particle size distribution of a powder ensures a non-uniform dissolution rate, non-uniform sedimentation rate, uniform dissolution rate. So what it means is that, like if the consider the particles in a system, like in a, you are having a certain particles. If the size distribution of the particles is very uniform, we can say that when we are dissolving it in a solvent, the dissolution rate would also be uniform. Like it would, and it can also sediment uniformly. Like if the initial thing itself is uniform, the whatever the thing we are trying to do, that would also be a uniform thing. There is no chance for the dissolution rate to go non-uniform or sedimentation rate to go non-uniform. So the answer to this is a uniform particle size distribution of a powder ensures a non-uniform dissolution rate. It is a false. Non-uniform sedimentation rate, it is again false. Uniform dissolution rate is the right answer, and it is not none of the above also. Okay, so we just move on to question 12. The continuous rubbing or grinding of the powder in a mortar with pestle to reduce the particle size is called pulverization by intervention, trituration, litigation, none of the above. For example, if you would be doing this in a, like you are grinding something in a mortar pestle, wherein you are rubbing and then grinding by means of thing, right? So what is it called? It is pulverization by intervention, trituration or levitation or none of the above. So the answer to this is trituration. So we'll just see what all these three terms denote first, and then we'll come to the conclusion. So pulverization is the process of applying an external force, uh, by applying an external force to a material of a certain size to destroy it and reduce it into pieces that are smaller than the original size. In trituration is the name of several different methods to process the materials. It is a form of comminution. Comminution is nothing but breakage of particles or like reduction in size of the particles. It is a production of homogeneous powder material by mixing and grinding component materials through thoroughly. And in levitation, it is a process of grinding an insoluble substance to a fine powder while wet. The material is introduced into the mill together with water, in which the powdered substance remains suspended and flows from the mill as a turbid liquid or thin paste according to the amount of water employed. So we'll just go one by one. Pulverization is the process wherein we apply an external force so that it gets reduced in size, and it becomes smaller than the original size. Like whatever the means, like crushing, grinding, everything comes under this. In trituration, it is also a comminution process wherein we produce a homogeneous powder material wherein we mix and then grind. It is similar to the mortar and pestle, right? Mortar and pestle, consider, we all have that in kitchen, right? Wherein we just do something like put one or two items in the small mortar and use pestle to grind that, and we have a uniform homogeneous powder. So trituration is the process of producing that uniformed powder by means of mixing and grinding component materials. Like in the old grinder and all, there would be like uniform mixing and grinding, right? But in litigation, it is a process of grinding an insoluble material to a fine powder while it is wet. So wherein we introduce the substance along with water, and then it depending on the amount of water, it flows as turbid liquid or thin paste, whatever it is, but it is a wet process. So the answer to this is trituration, wherein we rub and grind, thereby we produce a uniform mixing and the grinding of the particle also takes place. So yeah, before moving from question 13, let us just take a 5 minutes break. We'll just start the session by 7 2 sharp. So like everyone, like we will take 5 minutes break and we'll reassemble here by 7 2. Yeah. Yeah, I hope everyone is back. We'll just start the session now. According to GELDAT classification, flour, cement are the example of the powder of the type. So basically what GELDAT classification means is that it classifies the particles into four categories: A, B, C and D, depending on the particle density difference and the diameter of the particle. So this is rho p minus rho f, that is the density of the fluid minus the density of density of the particle minus density of the fluid, and versus the diameter of the particle. So very low diameter particles are come under the GELDAT C category. That is, these particles are very small, they are cohesive in nature, that is they stick together, and it is very difficult to fluidize such particles. And GELDAT A, this is aeratable particles. These are comparatively larger in size than GELDAT C particles. Still, it is kind of difficult to go with the fluidization of A particles. And next is the GELDAT B particles, that is sand-like. They are comparatively larger in size and is significantly easier to fluidize these particles. So most of the fluidization application, if you see, they are going with the GELDAT B particles. And the last category is the GELDAT D particles. They are very small, larger particles. The thing is, with B and D, there are chances for the bubbling fluidization to take place. The bubbles forming would be very predominant in the B and D particles, wherein it is very difficult to fluidize C and A particles. So, if we consider flour, cement and all, they are very smaller particles and there are chances of it sticking together, right? So, they come under the type C. That is option C, type A, B and C and D. So, the answer to this is option C, that is GELDAT C particles uh, include flour, cement, etc. So drag coefficient in the turbulent flow regime is equivalent to, so actually uh, the like when we are fluidizing the particles, the fluid drags the particle, right? So the drag force experienced by the particles would be there. For example, in the question one, yeah, like if the drag force is exceeding the gravitational pull of the particle, the bed starts to behave like the fluidized bed. So in order to quantify the drag force, the drag coefficient is used, wherein it is depending on the laminar flow regime and the turbulent flow regime. So in the turbulent flow regime, the answer is option A, that is 0.44. This is like you would have studied in the fluid mechanics for the laminar flow and the turbulent flow, how the drag coefficient is varying for the packed bed or the fluid bed where the particle fluid interaction takes place. So that in the turbulent flow regime, the answer is 0.44. Whereas for the laminar regime, it is calculated by using Stokes law. So the what drag coefficient compares gravitational and inertial force is option A. Option B, it is viscous force and inertial force. Option C, it is inertial and capillary forces. Or option D, it is none of the above. So in the previous thing also we saw how drag force affects the gravitational also, like how when it exceeds the gravitational pull, the bed starts to act as fluidized bed. So drag coefficient it is denoting how much drag force is required to pull the particles, right, against the gravitational act. So it is gravity and inertial force. For example, this is the drag coefficient is the drag force by rho u square by a by 2. So we can see that it is the measure of the gravitational force and the inertial force. So answer to this is option A. Now we'll just move to the next question, that is question 6. If these common like drag coefficient thing does not come in week 1, I am not very sure whether it is covered in the week 1 lecture or not, but it would be useful in the further lectures also. So just look into it. Don't go in depth into it right now if it is not covered in the syllabus. So attrition, what is attrition? That is question 6. Attrition is the collapse of dilute phase suspension into a dense phase flow, breakdown of particles, tendency for fine particles to be preferentially entrained from the reactor, none of the above. So attrition is nothing but when we are rubbing the particles and reducing the size of the particles. For example, um, I like what to say, but it is in general it is the breakdown of particles is the attrition. Example, what can we say? Like when we are using a vessel and we are putting some particles into it, and like we'll take grinding itself, where like we are grinding the particles by placing it between two walls, like that is a grinder and the vessel wall or something. When it is moving, that is the inside thing is moving, the particles, and one particle comes in contact with the another particle, right? So when two particles come into contact with each other, or even when the particle goes in contact with the wall, the energy is getting dissipated, which in turn acts to break the particles. So in general, it is the breakdown of particles is known as the attrition. And we'll just move on to question 17. Question 17, segregation is the property of particles to gather in different zones according to their size and density, to be preferentially entrained from the reactor, to fall through under gravity, usually with co-current flow, all the above. Okay. What is segregation? Segregation is just separation, right? For example, in fluidization, if you consider the particles with different size behavior or different density behavior, the chances are, like in general we know, right, the lower density particles would go up, and the higher density particles or higher size particles, there are chances of it settling down. In general, that is the case. So um, uh, like depending on the zones, or depending on their size and density, how it is getting uh, segregated, that is gathering. To gather in different zones according to their size or density is known as the segregation. Segregation is the property of particles to gather in a different zones according to their size or density. Answer is this one. Like this is studied exclusively. That is, segregation phenomena is studied exclusively based on density difference and the size difference. How the particles behave in the system. That is how it is segregating, how it is separating. For example, in fluidized beds, there are provisions where the particles will be segregated based on size or density, so that at different levels or different zones the particles will be collected and analyzed. For example, consider this is the bed, like the depending on the size density the particles, when we pass fluid, the particles would be moving, right? So depending on the size or density, they would be moving differently. So there are trays for collecting, the provision would be made for collecting in terms of trays. So depending on that, the particles would be collected and analyzed. So this is segregation. Segregation is the property of particles to gather in different zones according to their size or density. We'll move to question 8. At very low gas flow rate, frequency and size of the bubbles formed are primarily governed by. So actually I told you that when we pass the fluid into the particle bed, the particle starts moving. So when the particles, like when the velocity is very much excess of the particles, the bubbles, I mean the particles start moving, and if it is very difficult for the particles to separate, there are chances that bubbles would be formed in the bed at very high gas flow rate. Like when it is impossible to separate the particles, they would move together and it would result in the formation of bubbles. All these things would be studied in the further lectures. So what governs the formation and the frequency and the size of the bubbles at very low gas flow rate? Very low gas flow rate. The one thing is surface tension of the liquid and the buoyancy force of the bubble. It like how it is preventing the particles to move separately, or how close the particles are sticking together, and how the bubble as a whole, like what is the surface tension of the liquid and how it is making the buoyancy and like how it is making the bubbles to move. All these denotes or governs the frequency and the size at which the bubbles are getting formed. So the answer is option A is also right, option B is also right. So answer is option A and B, that is option C is the right answer. That is the frequency and size of the bubbles formed are governed by surface tension of the liquid, buoyancy force of the bubble. All these are the right answer. I mean both of them governs the formation of bubbles. So again this is a drag coefficient thing. Like general statement is that CD would be 24 by RE into something for the Stokes regime, that is laminar flow regime, or in turbulent regime it is 0.44. This one we already saw. And for the Stokes law regime or laminar flow, the answer is 24 by RE. So the question, we'll just go on to question 20. A spherical particle is settling through a stagnant column of liquid. The terminal settling velocity of the particle is proportional to diameter of the particle, proportional to the square of the diameter of the particle, proportional to the cube of the diameter of the particle, none of the above. So what it is asking is the terminal settling velocity formula. So most probably this would have been studied as a part of fluid mechanics for studying the terminal settling velocity. So if you remember the terminal settling velocity formula, Vt is directly proportional to dp square or something. Vt, that is terminal settling velocity, is proportional to dp square. So actually, okay, u is answer is proportional to the diameter of the particle. So this is option B. And we'll just move on to question 21. Advantages of fluidization process are. So this is basically coming back to the original thing. What are the advantages associated with the fluidization process? Just a minute. Actually, the answer for the previous one is BT. Rho P minus rho F 18 mu. So actually it is proportional to dp square. So the answer is option B. So coming back, we are back to what is the advantages of fluidization process. So we know that it is has good mixing. Good mixing, it is the correct answer. It is having more contact efficiency. The contact efficiency is improved in fluidization. It is not having less contact efficiency when we are dealing with the fluidization process. So the answer option B is wrong. Batch operation, again this is wrong. We can do continuous operation of the fluidized bed. One, because it is obviously used in industries where large scale continuous operations are being taken place. Like we pass the fluid inside the system, and if it is exceeding the velocity, the particles would be escaping from the top, wherein it would be collected separately and then recirculated back. So all these things are still there. So the answer is false. So the only correct option is option A, that is good mixing. It is offering good mixing, right? So advantages of fluidization process is good mixing. Okay. At minimum fluidized condition, the pressure drop through any section of the bed is equal to. Okay, these questions are taken from, actually, okay. These are just practice problems. So if you are interested, you can just solve these. Yeah, just for general knowledge. At the minimum fluidized condition, the pressure drop through any section of the bed is equal to weight of fluid and the particles in that section. For example, if we go about in this, yeah, what is fluidization? At minimum fluidization velocity, as we discussed before, below the minimum fluidization velocity, when the fluid is getting passed through the particles would remain in the fixed position. I mean, it would be, the particles would not be moving. While after the minimum fluidization velocity, the particles would be starting to move. What happens at minimum fluidization velocity is that the particles would be suspended in they would be suspended in the fluid medium. The pressure drop would be equal to the weight of the fluid and the particles in the system. So the answer is the weight of the fluid in the system in that section, weight of particles in that section. The answer is weight of fluid and the particles in that section. So at minimum fluidization velocity, the pressure drop would be equal to that. Thereby the particles would be getting suspended in that fluid. They would not be moving, but they would not be close packed also. They would be suspended. Question 23. Terminal velocity of a particle. Terminal velocity can be found from balancing the forces, gravitational and inertial forces per unit volume, gravitational, buoyancy and drag force per unit volume of particle, gravitational and drag force per unit volume of particle, none of the above. How do we get the terminal velocity? Wherein we equate all three forces, right? It would be gravitational force acting on the particle, and the buoyancy force, and the drag force acting on the particle. When we balance all these three, we would be getting the terminal velocity of the particle. Can be found from balancing the forces, gravitational, buoyancy and drag forces per unit volume of the particle. So the answer to this is option B. At the onset of fluidization, void is, what is the void age at the onset of fluidization? This question also we discussed right now. Like the particles would be starting to move, that is the bed would be expanding, right? So what is void age? Void age is the void fraction of the system, right? So when the particle starts moving, what happens? The void age is increasing. So but in the packed bed, the void age is very less compared to the fixed bed, right? So the answer is, at the onset of fluidization, the void age is larger than that of the packed bed. Whereas like in the packed bed, it would be like this, the particles would be very much closely packed. Whereas in fluidized bed, the particles would be moving, right? So the void fraction in the bed increases. If we take this particular region of the bed compared to this particular region, whereas here the void fraction is less, here the void fraction is more. So larger than that in the packed bed. So the answer to this is option A. So for our understanding, this is a picture explaining the fluidization regimes. This is taken from the Cooney and Levenspiel book. So this is one of the reference book. So we'll just understand what is happening with the help of this diagram. So we are passing the particles are packed inside the bed. So this is the bed height. LM is the bed height. Then we pass the gas or the liquid, that is the fluid, at a very low velocity in the fixed bed or packed bed. In the fixed bed, the particles would not be starting to move. That is, the particles would be very tightly packed. When we increase the velocity, this is with increase in velocity. When we increase the gas or the liquid velocity, the particles would be suspended in the fluid medium. They would not be moving, but it would be suspended. This is known as minimum fluidization velocity or minimum packing length or minimum packing height. This is minimum fluidization velocity. For example, this is considered as a liquid you are passing, where with further increase in the velocity of the liquid, the bed starts moving. But as you can see from this picture, the movement is uniform. There is no bubble formation or anything. The particles are getting very uniform movement. So this is not a smooth fluidization. So, but if it is a gas, the particle starts moving and bubbles start to form. These are all bubbles. So this is known as bubbling fluidization. With further increase in velocity in the gas, the particle starts to move, and the bubbles also starts to grow in size. This would be like they would be growing in size, and they are kind of occupying the end, almost the column length, as you can see. Sorry, column diameter. So this is known as slugging or axial slugs. Whereas in flat slugs, we can see that it is almost occupying the entire diameter of the column. The bubble starts expanding and occupies the entire diameter of the column. This is known as flat slugs. With further increase in the velocity with the gas fluidization, what happens is that the bubble starts to break and very turbulent regime is observed. Turbulent fluidization takes place and the bubble starts to break and there is very turbulent regime, like it would be chaos inside the bed. This is known as turbulent fluidization. And at last is the lean phase fluidization with pneumatic transport, wherein the particle can escape from the system and they would be recirculated back to the bottom. But as you can see, only few particles are present in the system, right? Because all the particles are transported, that is lean phase fluidization with pneumatic transport. This would be used to transport the particles. Like as you can see, very few particles are there and all the particles are moved to the top. So the velocity is that high. As you can imagine, that much high velocity is used so that the particles can be transported from one area to other. This is known as lean phase fluidization or the pneumatic transport. These are the fluidization regimes. Mm, like different phenomena observed when we increase the fluid wall velocity. So next we move on to question 25. In case of homogeneous or particulate fluidization, as gas velocity increases, bed expands smoothly in a homogeneous manner. Further increase of gas velocity, bubbles are formed in the bed. Actually, the answer to this would be none of the above. Sorry for the confusion. Because bubbles won't form in the particulate fluidization or homogeneous fluidization. Like, but this homogeneous or particulate fluidization happens with the liquid fluidization, so that when we increase the gas velocity, when we increase the liquid velocity, the particles moves smoothly. There is no bubble formation, or there is the answer is this one is right, but it is not associated with gas velocity actually. I mean, it is not associated with gas, because when gas is passed, right, it would be moving very fast. The chances that it is going fast is very strong. So um, it is not a homogeneous fluidization, rather it is heterogeneous fluidization with bubble formation and all. And since it is bubble formation, it is not homogeneous. So the answer is option D, none of the above. We'll just move to question 26. In case of bubbling fluidization, bubble size increases as gas velocity increase. Bubble size decrease as gas velocity increase. Bubble size remains unchanged as gas velocity increases. None of the above. So as we can see, with increase in gas velocity, the bubble size that were smaller over here are increased in size. This is the turbulent region, that is a completely different phenomena. But in general, when we increase the bubbling, in the bubbling fluidization, when we increase the gas velocity, the bubble size also increases. So the answer is bubble size increases as the gas velocity increases. So the answer to this Answer to this problem is option A. That is, bubble size increases as gas velocity increases. So in fluidized bed, the particulate regime with further increase in fluid velocity, the pressure drop across the bed increased decreased remains constant. Actually, the thing is, in the fluidized bed at the particulate regime with further increase, this is also answer should be option C. Because sorry, yeah, when at the particulate regime, because it is a fluidized bed, what happens is that in fluidization with increase in fluid velocity, let this be fluid velocity and this be pressure drop. When fluidization superficial gas velocity and superficial fluid velocity is increased, the pressure drop keeps increasing till it is a fluidized bed, sorry, till it is a fixed bed, after which at minimum fluidization velocity the pressure drop and the weight of the particles in the fluid becomes equal, right? So this is the point of minimum fluidization. After the fluidization, the minimum fluidization, like after minimum fluidization, how much ever we increase the fluid velocity, the pressure drop remains constant. So the answer is option C. The pressure drop across the bed remains constant. In case of churn flow, spherical bubbles are formed, distorted bubbles are formed, bullet shaped slugs are formed, none of the above. So, what is like we saw in this, right? Churn flow is just this. Like after flow slugging bed, it becomes distorted, right? So the bubble formation pattern with increase in fluid velocity does not remain the constant. So we cannot say the bubbles should be spherical in shape. Like the bubbles on with increase in the fluid velocity, the probability of distorted bubbles to form are more than the spherical bubbles. So in case of churn flow, sorry, question 28. In case of churn flow, spherical bubbles are formed. We cannot say that. Distorted bubbles are formed. Bullet shaped slugs. These are all the, like, we cannot identify or we cannot predict the shape of the bubbles that is found in case of churn flow. So the answer to this is, in case of churn flow, distorted bubbles are formed. Okay, just a minute. So yeah, in case of churn flow, distorted bubbles are formed. So yeah, thank you. These are all the questions for this week. Like these are general questions that have been taken from this week. So if in case, yeah, so these are the general questions that is covered for week 1. In the coming weeks, we will identify more problems that are specific to that week's lecture. So since it is a first week and introductory session, the problems are generally covering all aspects of fluidization and the different fluidization phenomena and the different particles properties associated with them. So the actually, if you people have any questions related to this week's content, or that is the problem, the 28 problems that we saw just now, if you have any questions in these problems, you can always ask. Like you can ask now. If you have any questions, please feel free to ask now. Yeah, once again, yeah.
The question.
Which question?
27.
Okay, yeah.
Actually, investigation study uh,
Actually, I cannot hear you. Can you just put it in chat box? I'm not able to hear you. Yeah.
actually in Bernoulli's equation we have studied like pressure is inversely proportional to velocity. So when the velocity increases, the pressure decreases. I don't understand the graph.
Okay, with hello. Okay, just that is that is the case when the velocity it is in a open system, right? Here the particles are also present in the system, right? Like here the particles are also present over there. So the gas velocity that we are denoting is actually the superficial gas velocity. So when the gas is passing through that, uh, like it would be passing through the gap between the particles only. So with uh, like when the bed is fluidized, the particles would be moving very freely. So like the pressure drop would remain the same. There is like no provision for it to further increase. Like it, I mean the system would more or less remain the same. Like it since the particles are suspended over in the air, the velocity of effect would not be there actually. Or else how to say once again. Actually, it is the bed. Like it depends on the particles present in that area. So, like after minimum fluidization velocity is crossed, like the particles would like it remains a constant. There is mm,
Actually, if we
yeah.
close the container, then the pressure can't be remains constant. Otherwise, if we open a container, actually, if the container has a hole on it, then we can only adjust the flow. But I think we can't set the pressure in
I mean,
constant.
it is a open container only now. If that is,
Yeah, but
yeah.
in the open container, we can only set the flow, not the pressure. I think so.
I mean, here we are not setting anything. Actually, the thing is, if the particles are closed packed, like when with further increase in the fluid velocity, like till some point, the particles would be very tightly packed. There is they would be sticking together. So the pressure would keep on building up till that point. So after it is so at that before in the fixed bed regime only the pressure drop increases. after which it remains constant for maybe I'll explain this in more clarity in the next class. Like, I am not sure how to explain it to you in simpler terms. But basically, the
Yeah,
concept
okay.
is with increase in the fluid velocity, because the particles get loosely suspended, the pressure drop would remain the same. That is, the fluid would easily pass through the system, so the pressure drop variation across the system would not be that significant.
Okay,
Mm.
we have studied in like when using Bernoulli's theorem, we have studied like when the pressure decreases, the velocity increases. Uh, it is also used in the fluid mechanics concept, like in nozzle, when the velocity increases, the pressure decreases. That's what I'm saying.
Yeah, but that would be with only fluid inside the system, right? Here, another concept of particles also comes into picture, na. So the particle location and the particle weight, the particle movement also in turn affects the fluid velocity. I mean, in turn affects the pressure drop and all. So, or just um,
Yeah, okay. I think I'm also not sure about it, but just a doubt.
yeah, actually, the thing is, this is what happens, but I'm not sure how to explain it to you. That's what, give me some time. I'll give you the answer in the next class in a more clear way.
Yeah, okay.
Yeah.
Uh, I have other. Wait,
Yeah. Hmm.
okay. Um,
With
24th question.
24. Okay.
24.
Okay. Yeah.
Uh, could you explain that meaning of the word onset of fluoridation?
This is just,
Is it a starting stage or the in the middle of something?
yeah, starting stage also. Like once
Uh,
fluidization start.
yeah, okay. And
Hmm.
then next page,
Hmm.
you just
Hmm.
uh, in the second diagram, when the minimization fluoridation occurs,
Yeah.
the minimum velocity,
Hmm. Hmm.
the void between the two particles is so well, how it can the but the answer is larger. You see,
Yeah, here the voidage is more, right?
compared to the
Fixed
A
bed.
diagram, the
Yeah.
B diagram has a
More
yeah
voidage.
yeah
I mean, that is what is given, right? At the onset of fluidization, the voidage is larger than that in a packed bed. Here also that is the case. I mean, at the onset of fluidization, the voidage is larger than that in the sorry, larger than that in the packed bed or fixed bed.
so in the fixed bed, you already said like that
Hmm.
they are in a closely packed manner. After we pass some
Hmm.
velocity, it separates into some voids.
Yeah. Hmm.
The actually the definition of a void is the gap between two particles. Am I right?
Not the exactly the gap. Void is just, I mean, it is the gap actually, but yeah, you can say that. For example, I'll just give, consider this, okay, this region alone. For in this region, there are more number of particles. So the volume of the particles should be more, right? In this
Yeah.
particular. So in the total volume of the bed, let us take it volume of bed. In a similar fashion, here if we take this volume of, okay, we'll keep volume of particles A, volume of particles in B,
Okay.
and the volume of bed remains same, like I am taking only the same volume. Here volume of particles is more, it is less, VPB is less. So what is voidage in A? It is 1 minus this fraction, right? Let us keep it A, let us keep it B. 1 minus A is the void fraction or void edge. Similarly, 1 minus B is void fraction in B. So which one would be more? Since this B is less, 1 minus B is more, right? So the void edge is more at the onset of fluidization.
Yeah, okay. Uh, Another like the sphericity value, question number 8.
Okay. Sphericity 8. Yeah.
Here the sphericity value,
Hmm.
could you explain another time?
Okay,
Repeat.
actually, what sphericity means is consider a particle, this is sphere, right? And if this is cube, in general, what sphericity means is how much the non-spherical particle resembles the spherical particle. So obviously, the sphericity for the spherical particle would be 1 because the spherical particle resembles spherical particle as such. But in general, how we calculate for consider a cube, the sphericity for the cube would be here the surface area of a sphere that is having same equivalent volume diameter, sorry, same equivalent volume as that of the cube. I mean, we are considering the from the cube volume we are calculating a sphere which is having the same equivalent volume. So for that sphere we are calculating the surface area divided by the surface area of the original particle, that is surface area of the cube. That would be cube surface area. So from this, what it can be like, but for this question, the question asked is for a spherical particle, what is the sphericity value? So the question is, and like here also, now the what comes is surface area of sphere by surface area of sphere, because both are same particles, so it is 1. Did you get that actually?
But uh, the previous the sphericity value formula spherical equivalent volume by the NSP non-spherical.
Hmm.
So the sphericity value for a spherical solution, right?
I'm sorry, but your last part of the question I could not hear you.
Actually, the sphericity value formula you have right in a previous, like sphere equivalent volume divided by a non-spherical particle.
Yeah, yeah,
Is that correct?
yeah, yeah.
Um, the surface area divided by volume of the particle, and
Yeah, actually, this
the
is
same
surf.
for
Yeah, this one is the top portion is for the surface equivalent, like the volume equivalent sphere. We are calculating one volume equivalent sphere. The top portion belongs to that volume equivalent sphere calculation, and the bottom is for the original non-spherical particle. So this is just a phenomena to calculate how it resembles spheres, and it would be less than 1. Yeah.
Excuse me, can
Yeah.
I leave?
Yeah, if your questions are like answered, you can leave. Yeah, the session is that's it.
Yeah, thank you.
Yeah, thank you. So that's it for today's session actually. In today's class, we just saw a few problems associated with the fluidization course in the first week lecture. So we saw discuss overall about the fluidization process and different terminologies associated with the fluidization, and then we saw few parameters like sphericity, circularity, and so on to define the non-spherical particles shape. And then we saw few regimes of fluidization like bubbling fluidization, like different smooth fluidization, particular fluidization, bubbling fluidization, slug regime, slugging regime, churn fluidization, and pneumatic transport or the lean fluidization, lean phase fluidization. So depending on the application that is required, we just go for this. So that's all for this week's session. So I just thank everyone for attending, who has attended, and this since this is the first week, with following weeks we'll understand more in depth into this. We'll go more in depth into all these concepts. So at that time the understanding would be easier for us. So although the uh, assignments are open in the class, so please make sure that you are answering the submitting the assignments on time if you want to appear for the exams, and also make sure you're on time with the exam registration also. So yeah, thanks everyone for attending. Please feel free to ask any questions if you have, and if there is any doubt in this week, please consider asking in the next class. I'll be happy to take those questions in the next class when we meet. So yeah, thank you, thanks everyone. Thank you everyone. Thanks for attending. We'll meet again the next Friday, the same timing from 6 p.m. to 8 p.m. So since it is 7:51, yeah, we can close the session. Thank you, thank you. We'll meet in the same time next week. Yeah.